Welcome back to the deep dive. Okay, so you sent us looking into a really interesting one this time, Amygdalodon. Maybe not a household name, huh?
Not like T-Rex, no. But definitely important. We've dug into the science, the papers.
Yeah. And our job, as always, is to pull out the really cool bits, the stuff that makes this dinosaur significant in, the grand scheme of things.
Exactly. You want the insights without getting buried in jargon. So let's get straight into Amygdalodon patagonicus.
Right. Amygdalodon. The name itself is usually a good starting point.
It is. Amygdalodon literally means almond tooth.
Almond tooth. Okay, simple enough, I guess because of the shape.
Pretty much, yeah. Named for its almond-shaped teeth. But the discovery story is actually quite something.
Oh, how so?
Well, think about Argentina before 1936. Today, it's famous for fossils, right? Especially dinosaurs.
Sure, loads of titanosaurs and things.
Right, but back then, zero sauropod fossils known from the entire country. None.
Wow, okay. That's hard to imagine now. So what changed?
Well, there's this mention by a geologist, Piatnitsky, of finding some small saurian bones. Just a little note.
Like a footnote almost.
Kind of. But it caught the attention of Dr. Suero, and he decided to follow up.
I think he did.
Absolutely. His team went to the Pampa de Adnia region in Chubut province, and they found something much bigger than expected.
Ah, so not the small bones Pete Niski mentioned.
Maybe related, maybe not, but what Suero found was undeniably a large sauropod, a Jurassic one, which was also unexpected, and roughly double the size they might have anticipated finding if they found anything at all.
Double the size. That must have been a shock, a really good shock, I imagine.
Oh, definitely. A paleontological jackpot, like you said.
Yeah.
It completely changed the picture, suggesting these big guys were around in South America earlier than people thought.
So what did they actually find? What's the main specimen?
That's the holotype, MLP 46.821-1. It includes some vertebrae, bits of ribs, crucially, those almond-shaped teeth, complete and partial ones, and even parts of the pelvis and a shoulder blade.
Okay, so enough to get a decent idea of the animal.
Enough to know it was something new, yes. And there are other bits too, the type and lectotype specimens labeled A through H and I through O, documenting those initial finds.
And then someone had to formally describe it, right? Give it the official name.
That was Cabrera in 1947. He published the description of Amygdalodon patagonicus, putting it officially on the scientific map.
Patagonicus for Patagonia, obviously. Makes sense. Okay,
Yeah.
so we know what it is and how it was found. When and where was it actually living?
Okay, time-wise, we're talking Middle Jurassic, specifically the Torsion Age. That's roughly 180 to 172 million years ago.
Middle Jurassic, so quite a bit earlier than giants like Brachiosaurus or Apatosaurus.
Exactly, a more ancient branch of the sauropod lineage. And geographically, all the fossils come from the Cerro Carnero Formation in Argentina.
Right. Firmly South American. And you said it's one of the few Jurassic dinosaurs found there, still.
Relatively speaking, yes. Jurassic finds in South America aren't as common as, say, Cretaceous ones, or Jurassic finds in North America or Africa. So Amygdalodon gives us a really valuable peek into that specific time and place.
Okay, let's picture this thing. How big are we talking?
Estimates put it around 12 meters long, which is, what, about 39 feet?
Longer than a bus. Decent size.
Uh-huh. And maybe 4 meters or 13 feet tall at the shoulder. Weight-wise, probably over 5 tons.
5 tons. Okay, that's substantial. Definitely a big herbivore walking on all fours.
Quadrupedal, yes.
Yeah.
Solid, ground-shaking kind of animal. But the really fascinating stuff, for me anyway, is trying to figure out its family connections. Where does it fit in the big dinosaur tree?
Right, the classification. Let's run through that quickly. We know it's an animal, has a backbone.
Yep. Eukaryota, Animalia chordata,
Yeah.
and Dinosauria, Saurischia, the lizard-hipped group.
Which includes both these long necks and the big predators. Always find that interesting.
It is counterintuitive, isn't it? Then Sauropodomorpha, the broader group, including ancestors, and then Sauropoda, the true long-necked giants.
Okay, so within Sauropoda, where does Amygdalodon sit? Is it clear-cut?
Huh. Not initially. Science is rarely that simple, right? Back in 2003, a researcher named Rauhut looked at it and basically said, Sauropoda incertae sedis.
Incertae cities. Uncertain placement.
Exactly. Like, okay, it's probably in this advanced group called Sauropoda, but we're not sure exactly where it branches off. The evidence just wasn't strong enough to pinpoint its closest relatives within that group.
So a bit of a mystery guest within the Sauropod family.
Sort of, yeah. But then new studies, new methods things change. In 2010, Carbolito and his colleagues did a cladistic analysis.
Yeah.
That's where they map relationships based on shared features.
Right. And what did they find?
They actually placed it outside Eusauropoda as a more basal, non-Eusauropod sauropod. So an earlier branch on the sauropod tree before the Eusauropods really diversified.
Okay, so moving it to an older branch, more primitive in a way.
More early branching is probably a better way to put it. And that idea started to get more support. In 2018, Holwerda and Paul found it was possibly a sister taxon to Ionosaurus.
Sister taxon, meaning its closest known relative.
Pretty much, yeah. Like evolutionary siblings or very close cousins branching off near the same point on the tree. Ionosaurus is another early sauropod found in Thailand, actually.
Interesting. So potential links across continents, even way back then.
It definitely hints at that. And the story gets even more refined with research from 2022, again involving Pohl and colleagues.
Okay, what did they add?
They reinforced that basal sauropod position. But the really cool finding was about its biology, its adaptations. They saw that Amygdalodon had teeth showing early modifications for bulk feeding.
Bulk feeding, like just grabbing huge mouthfuls of plants.
Exactly. Shoveling it in. It's a key thing that let later sauropods get so enormous. But here's the twist. Amygdalodon had these early bulk-feeding teeth, but it didn't have the specialized vertebrae, the backbone features that you see in later, more derived sauropods, which were also linked to processing all that food and supporting huge bodies.
Ah, so it's like evolution trying things out. It got the teeth partway there, but the rest of the skeleton hadn't fully caught up yet.
That's a great way to think about it. An early experiment in becoming a giant plant processing machine. It shows these features didn't all evolve at once.
Fascinating. The source also mentions it being in a polytomy, with Gunxianosaurus from Asia and maybe related to Voltimeria from South America. What's a polytomy?
A polytomy is basically a point on the family tree where the relationships aren't fully resolved. It's like a fork in the road with more than two paths branching off at the exact same spot. We know Amygdalodon, Gunxianosaurus, and maybe Voltimeria are related, probably splitting off around the same time, but the exact sequence who split off first isn't clear from the current data.
Okay, so they're all clustered together on an early branch, but the fine details are still fuzzy.
Precisely. The potential link to Gunxianosaurus is interesting for that Asia-South America connection again. Voltimeria is also South American, but its own position has been a bit unstable in different analyses, so that connection is more tentative.
It really shows how science is always refining these relationships as more fossils turn up or analyses improve.
Absolutely. And that 2022 research really framed Amygdalodon in the context of this bigger picture. The early evolution of sauropods, and then the later major diversification, the radiation of the Euchoropoda, especially in South America.
So Amygdalodon is like a snapshot from before that big evolutionary explosion.
A very important snapshot, yes. It, along with others like Voltimeria, shows us what sauropods were like just before that group really took off. The source even lists a whole bunch of other early related sauropods, or near sauropods. Melanorosaurus, Lianosaurus, Lissosaurus, and Tatanitris, Volcanodon.
Wow, quite a crowd.
It paints a picture of real diversity even among these early forms, exploring different ways to be a large herbivore before the classic Eusauropod model became dominant.
And wasn't there some other material found later ascribed to Amygdalodon?
Ah, yes. Casmacoila referred some bones in 1963, a back vertebra with a rib bit, a sacral vertebra, and the end of a lower leg bone, a tibia.
So adding a few more puzzle pieces.
Every little bit helps flesh out the picture of this animal.
Okay, so wrapping up our deep dive on Amygdalodon, what are the absolute key takeaways for you, the listener?
Well, first, remember the name, Almond Tooth. Tells you about its teeth. Second, its huge historical importance as the first sauropod found in Argentina, a real game changer.
Right. And it lived in the Middle Jurassic, 180, 172 million years ago. Pretty big, 12 meters long, over 5 tons.
And crucially, its evolutionary position. It's a basal sauropod sitting on an early branch of the family tree. It shows us those fascinating early steps towards bulk, feeding the teeth were changing, but without all the advanced skeletal features of later giants.
Highlighting that evolution happens piece by piece, not all at once. And its relationships, though still being figured out, hint at connections across ancient continents.
Exactly. Which leads us to a final thought for you to ponder. Think about what this early development of bulk feeding in Amygdalodon tells us. What must the environment, the plant life, have been like in the Middle Jurassic to start pushing dinosaurs down this evolutionary path?
Yeah, what drove the need to eat that much vegetation? And how did these initial steps, seen in dinosaurs like Amygdalodon, set the stage for the absolutely colossal sauropods that came millions of years later? What pressures, what opportunities shaped this incredible journey toward gigantic size? Something to think about.